Hello everyone, welcome to this presentation. Today I will be talking about a paper I presented at EUSIPCO conference 2018 in Rome, Italy. My name is Alfredo Esquivel. This paper is called On Optimal Filtering for Speech Decomposition. This paper is co-authored with Jesper Nielsen and Mads Christensen from Aalborg University. So before starting with the paper, this paper has to do with a project which is entitled Signal Processing for Diagnosis of Parkinson's Disease from Noisy Speech, in which there is a database of patients who have Parkinson's disease and patients who are healthy individuals. And those files are, for example, about sustained vowel phonations in order to be able to diagnose them. It is also possible to remote assist if they have the disease or not, but normally those files, if they are recorded or if they are sent over a network, might be corrupted with some effects as reverberation or background noise. In order that the medical clinic can make a diagnosis, some signal processing algorithms are needed to be applied to the speech. So in this paper, we consider that there is background noise in the observed signals. So this is the agenda of what I will be presenting now. So I'm starting with an introduction in which I will also talk about the state-of-the-art methods, and I will explain the motivation of the approach we are using for the solution of the main problem. And then I will define which is the signal model and mathematically pose the problem in which we need at the next point to do some optimal filtering and statistics estimation. Basically, I will explain first the observed signal and stochastic part, statistics estimation, and then for the voice part. Then I will talk about experimental evaluation, in which I will say what is the motivation in why we did that way the experimental evaluation, what parameters we use for the experimental evaluation, some spectrogram analysis including some audio files, and finally some objective measures which allow us to compare with other methods. And finally, we conclude our developed work. So I'm starting now with the introduction. The decomposition of speech into its voice and non-voice components is important in many applications, such as speech coding, in speech analysis, in speech enhancement, in synthesis, and of course for diagnosing illnesses. For example, in the case of speech synthesis, a better quality speech can be obtained with a mixed excitation instead of a single excitation, as in the example of the voice fricatives as the Z consonant, which is actually better produced if excitation for the voice part and the voice part is considered more quality or natural sounding speech in that case. But the composition problem is going to be more challenging in the presence of additive noise. And this needs to be considered, for example, in remote voice assessment applications. So the consideration of the noise would be required for a proper diagnosis of voice pathologies. And also, the decomposition actually uses sustained vowel phonations to see if there is braided vowels or other forms of vocal dysphonia. But the component that is associated with braidness is also stochastic component, and also there is the noise component. So in this paper, we also kind of considering like that. So in the state-of-the-art methods, there are methods which select in a binary way the presence of voice and non-voice components per frequency band, such as the multiband excitation vocoder. But this is not very accurate from a speech production perspective. So there are methods which also consider that both components can coexist in the same frequency bands. And the most cited methods in this way are an iterative periodic and a periodic excitation decomposition, which here we denote ITER. And this method reconstructs the voice part excitation in the harmonic regions, which can be obtained by the Kjær, and also a method based on the pitch scaled harmonic filtering. Yes. And in our current work, We noted that these state-of-the-art methods do not differentiate between background noise and unvoiced pitch. These are two stochastic components which may be present at the same time. So basically, these methods are not robust in noisy conditions, and motivated by the way that optimal linear filtering has been used extensively for speech enhancement. In this paper, we take a first step in applying linear filtering to the decomposition of noisy speech based on the estimation of the statistics of the speech components. Now I will move to the signal model and mathematically formulate the problem. So we consider an observed signal vector of n most recent successive samples, in which the observed signal vector yn can be decomposed in a voice vector, unvoiced vector, and additive white Gaussian or color noise set of n vector. The sum of the voice vector and the unvoiced vector will form a speech vector. Yes. Okay, and we assume that the components of the speech signal, of the noisy speech signal, are uncorrelated. In such a way, the m by m covariance matrix of the observed signal can be expressed as the decomposition of the sum of the voice component covariance matrix plus the unvoiced component covariance matrix plus the noise covariance matrix. It's in equation number 2 with the respective definitions using the expected values. So the objective is going to be to estimate the components from the noisy vector y of n by applying two different optimal filters. So for estimating the voice component, we apply a filter, an FIR filter of length m to the observed signal vector, and then we get three components, one desired filter components and two undesired filter components. The same is with the unvoiced vector, but we apply another filter which is called HU, and the same we have an observed desired filter component plus two undesired filter components. And the problem is going to be to find the optimal filters HB and HU, which make the level of the desired components as much as possible, while passing the desired component with as little distortion as possible. Now we need to estimate the statistics that we had in this previous slide in equation number 2 in order to design these filters. So yeah, I'm passing now to the optimal filtering proposition and the statistical estimation of each one of the components. So we define the error signals, the error signal for the voice part and the error signal for the unvoiced part. And then we take the mean square error, and we have two criteria, JV and JU, which depend on the variance of the respective speech components and the covariance matrices. And yes, we take the gradients of these criteria in the first equation, equation number 5, with respect to HB, and of equation number 6 with respect to HU, and equate them to the 0 vector. And then we find the solutions of the filters, which are the classical Wiener filters, as in equation number 7 and equation number 8. We see that these filters depend on the covariance matrices. So we need to estimate these covariance matrices. Yes, so we're going to do that right now. So for the observed noisy signal, in order to avoid problems between frame transitions, we adopt a recursive approach as in equation number 9. So we have an RY with a bar in the top, which is the sample covariance matrix, which is in equation number 10. And we apply this kind of smoothing with a forgetting factor alpha y, which will depend on the previous observation frame. And we also take into account the current frame in order to avoid this transition between frames problem. We consider that there is problem non-stationary noise. So we estimate the statistics of the noise component from the minimum statistics principle. And from equation number 2, we saw that the components are uncorrelated, so we can estimate the unvoiced component covariance matrix as in equation number 11, by subtracting to the observed signal covariance matrix the voice covariance matrix and the noise component covariance matrix. So we actually lacking now the voice covariance matrix. So now this is according to the harmonic model. So yes, we see that the voice part satisfies the harmonic model, as in equation number 12. So the voice part can be expressed as a sum of L harmonics. Each harmonic has an amplitude AL, and the different frequencies are the multiples of the fundamental frequency. So we have up to L harmonics. Omega 0 is the fundamental frequency. AL is the real amplitude, and we have the corresponding phases, phi L. And we can express the voice vector in that way with a set matrix times an amplitude vector A, in which the set matrix is formed by this complex exponential vector at the multiples of the fundamental frequency. Since we are handling the signal model, we need in conjugate pairs. And we need to estimate the amplitude vector, which is using a linear least squares formulation. And because speech voice component may be also non-stationary across a segment, we smooth the covariance matrix. So basically the RV bar is given by set P set Hermitian, and we also smooth it with respect to the previous frame by considering a forgetting factor alpha B. And for this matrix we need the P matrix, which is the covariance matrix of the amplitudes. In the real case is given by 1/4 of the diagonal of the squared amplitudes repeated 2 times. Then I will detail about the experimental evaluation and all the parts, the motivation, parameters, spectrogram analysis, and objective measures. Okay, so we know that the state-of-the-art methods evaluated their performance in a quantitative way only for synthetic speech signals, since the argument is that the individual speech components are not available separately for real speech. So in this paper, we consider an intermediate approach in which we mix fully voiced utterances, which are given in the down part, 1 female and 4 male, from a Cook database, and fully unvoiced utterances, which are these 4 or 5 phonemes, to have a ground truth knowledge. The mixing of both of them may not sound as natural as in common speech, but it will allow us to compare at the decomposition performance. So the parameters we used for the filters were the next ones. So we use a sampling frequency of 8 kilohertz, segment length 200, and filter length 25. We consider 3 types of noise: white Gaussian, straight noise, and bubble noise. And we evaluated the performance adding these 3 types of noise from -5 to 12 dBs. And we estimate the fundamental frequency in the interval 65 to 300 Hz using a maximum likelihood algorithm, which is a fast nonlinear squares method. And in color noise, this method would not be the most efficient because it assumes that the observed signal is buried in white Gaussian noise. So some kind of pre-widening has to be applied before estimating the fundamental frequency. And we apply an LPC pre-widening of order 5, as suggested in this paper, for the case of street and bubble noise scenarios. Okay. So this is an example of spectrogram of the true voice component, the true unvoiced component, and this is the sum of both voice and unvoiced component. So let's see how does it sound, the true voice component.
Why were you away a year, Roy?
Yes, the true unvoiced component. The concatenation of 4 consonants, which are unvoiced stops, for example. This is the sum of these 2 signals, which is actually the clean speech signal.
Why were you away a year, Roy?
So this signal, although it may not sound natural, has the true voice component plus the true unvoiced component. And then, for example, this is an observed signal with bubble noise at 4 dBs.
Why were you away a year ago?
Yeah, so now we will decompose this noisy signal, which has the three components, and give an example of the spectrograms. Okay, so the top spectrograms correspond to the voice component and non-voice component from the proposed approach. So let's listen to the voice component.
Why were you away a year ago?
Let's listen to the voice component.
Why were you away a year ago?
So we can perceive the different voice components, and we can see that this spectrogram has similar patterns to the ground truth. Yes, let's listen to the voice estimate from the iterative method.
Why were you away a year ago?
So it sounds kind of distorted, and actually it produces more harmonics, which were not present in the original signal, the original voice component. Actually, the pitch is estimated from the Kjær's room, and that estimation is not robust in noisy conditions. And for example, a non-voice estimate from the pitch scale harmonic filter method is quite like this, and we can see that more component is produced from the ground truth. And actually it has to do because the algorithm only estimates from stochastic and deterministic components. So everything that is stochastic is estimated here, which also include part of the bubble noise. So let's listen how does it sound.
Why were you away a year ago?
So part of the bubble noise is still here, and in some cases even we can perceive some of the original sounds. We can also have some component of the noise, which is the stochastic part. So yeah, the methods of the state of the art are not robust in noisy conditions. And here, even if in the voice component we have some noise, we can see that the features of the voice component are more preserved with respect to the ground truth. Yeah. So here we have an experimental evaluation in which we use objective measures as log spectrum distortion, Itakura-Saito distance, and segmental SNR. The top part we consider for the on-voice part, and the down part is from the on-voice part. So the red curve is about our optimal filtering approach. The blue curves correspond to the iterative approach, and the black curve to the pitch scale harmonic filter method. Also, we consider the noisy speech as an estimate in order to see if our method performs better, or all the methods perform at least better than no doing any processing of the noisy speech signal. So for the log spectrum distortion, a lower value, it's better. So for the voice component, actually our method is much better in this measurement with respect to the state-of-the-art methods. With respect to the voice component, we can see that it's very similar to the pitch scale harmonic filtering method, and it's actually better than the iterative method. In the Itakura-Saito distance sense, which is actually a more perceptually meaningful measure, we can see that the voice Itakura-Saito distance is much lower with our proposed method. And for the voice component, is actually better at low SNRs below 5 dBs with respect to the other two methods, and is very close, of course, at greater ISNRs with respect to the other two methods. But for high noise conditions, we see that our method is much better. And segmental SNR for the voice component, we can see that our red curve is above the noisy speech as an estimate, which is a good sign of it. Actually, it makes sense because our method considers both noise and unvoiced as stochastic components, and the other two methods reside below the green curve because they don't make this differentiation. So it will produce actually more component than the ground truth. And for the voice component, we see similar results with respect to the pitch scale harmonic filtering method, and better than the iterative method. Yeah. So I will conclude our presented work, and we consider the speech decomposition problem using the optimal filtering principle with the corresponding statistics estimation of each speech component. We used informal listening tests, spectrogram analysis, and objective measures to show that the presented approach works well. The proposed approach seems to be robust and convenient for speech decomposition in noisy conditions. Even if the low spectrum distortion at segmental SNR is similar to the pitch scale harmonic filter method for the voice speech component, we got lower Itakura-Saito distance values at low SNRs. And with the presented approach, the different on voice sounds as S, F, sh can be perceived. So thank you for your attention.